Okay, so we're doing exponential growth and decay, right? I've given you this formula here. Y equals A, B, X, okay? The A in this formula stands for the initial value. So we're talking about growth and decay. They'll probably tell you, we start with 5 or 5,000. That's what our A value is going to be. Our B value, when talking about growth and decay, is the growth and decay rate. Okay, see we have growth or decay rate. And the growth rate is 1 plus whatever the percentage growth is. And the decay rate is 1 minus the percentage decay. Now the reason we use the number 1 is because think of it like a percentage. Okay, if B was 1, that means that's 100% of the initial value. So if the initial value was 5 and B was 1, no matter how many times we put this to an exponent, we'll still only end up with 5. So that means there really is no growth or decay. We're a constant. 1 is our constant number. If we're above 1, we're going to increase in size because we'll be multiplying numbers like 2 to some exponent, and that'll move up. And if we're below 1, something like 0.5, oh, I forgot I can't do 0, or a half, that's going to bring our value down. That would be a decay rate. Okay? And X is the number of cycles or periods that occur over your growth or decay rate. So you had a question that said the number of bacteria in a culture doubles every 2 hours. Okay? So let's bring up another page here. So your question had said, there it is. Let's do this. Okay. So number of bacteria doubles every 2 hours. Okay, so here's our first question here. Number of bacteria in a culture doubles every 2 hours. The original number of bacteria is 6,000. Find the expression for the number of bacteria in 10 hours and in X hours. And when they talk about X hours, what they mean is the equation without anything in for the value of X. So we have Y equals, what were our letters? Do you remember them?
A, B, and X.
Yeah, so A times B to the power of X, right? So we have those there. What did A stand for?
Initial growth.
Okay, so if A was the initial value, what's our A value in this question?
6,000.
That's right, they started with 6,000 bacteria, so A in this one is 6,000. Now B is a tougher one. B stood for what?
Growth.
Growth. What did they say the growth was?
2 hours.
They said it doubles every 2 hours. Well, what's the actual, what's it growing by? How much?
6,000.
No, it's not.
Oh.
Well, you're right. The first time around, it'll grow by 6,000, right? So let's think about that. When it doubles, it grows by 6,000. I can't write zeros with that. But once it gets to 6,000, once we get to our 2 hours, we'll have 12,000, right? And then it's going to double again. So how much will that one increase by?
6,000.
That won't be doubling. Doubling means to take the initial amount and add whatever it is to it. So if we have 6,000 to start, then we have 12,000, let's say. We went up by 6. Once we're at 12, to double 12, we go up by 12 next. Then we'd have 24. So then when we double 24, we'd go up by 24, and we'd have 48. Okay? Do you see how it's going up by more than 6,000 every time? So doubling is an expression of like percent. 100% will keep us exactly the same, or the number 1. Doubling is like 200%. Okay? That means a growth rate of 200%, let's say. So in this case, our B value, do you know what it's going to be?
1.
Won't be 1, because that would be staying the same. If we're going up 200%,
2.
yeah. Oh. I see. Magic pen in different colors, my fault. There you go. 200% is also equal to the number, the decimal value of that would just be 2, right? Or 2. And in x hours means we're going to leave our number of periods as x. So what will this equation look like? Y is equal to what?
6,000
Yeah.
Times 2 to the power of 2.
Well, if it's x hours, what are we leaving it at? That's right. So there's our initial equation. Now, it actually asks us to find the expression for the number of bacteria in the culture in 10 hours. Okay? So, we have 10 hours. And at 10 hours, how often does this thing double?
Every 2 hours.
Every 2 hours. So, we're going to say 200% increase every 2 hours. So, how many times does it double in the course of 10 hours?
5.
That's right. We take 10 divided by 2, and we get 5. So our x value will be what?
5.
That's right. So now let's solve this equation. Y is equal to 6,000, 2 to the power of 5. So when we do BEDMAS, what do we do first?
Whatever's in the brackets.
Yeah. So 2 to the power of 5, so no. It's going to be the number 32. Okay. And then 32 times 6,000 is actually not that difficult. We got those zeros at the end. 6 times 2 is 12. Carry the 1. 6 times 3 is 18 plus 1, 19. So, after 10 hours, there will be 192,000 bacteria in this culture. Okay, so we have our y equals ABX. A is initial, B is doubling, or how much it's going up by, and X is the number of periods. Okay, well, in this one, our A, we actually don't know the initial value because we didn't start at 3 days. We assume we start at 0 days. So our A is actually unknown. What we do know is after 3 days, our Y value is 50,000. So I know I have 50,000 is equal to, we'll leave it as A. B is the percentage it's going up by, or the factor. What's the factor in this one?
300. Not 3 days.
Well, days would be a time frame. What is the what period? Doubling.
So 2.
Yeah, so that tells us it's going up by 2. Okay, and now X, we don't know how many periods this is. We don't know if a day is that or not. Okay, so we technically have 2 missing variables here. And our other one looks like this. 2 million is equal to, again, we don't know our initial value, but it is doubling. Okay. And we have X. So we have 2 separate equations. Now, what we can try to do here is manipulate the equation. Okay? Because since we know it is doubling, we just have to figure out how long it takes to double. Okay? So we're going to rewrite this question. Instead of writing it as 2 separate equations, we're going to write it as an initial period being, we're going to write our A value actual being 50,000. We're going to plate that in for our A value. And our goal is to get to 2 million. Okay? We're going to figure out how often it takes to get up there, or how many periods it has to pass. Okay? So our Y value, we'll do that in blue, let's say. Our Y value is going to be our 2 million. And our A value will be our 50,000. And we already know our B. So we'll rewrite this equation. We get 2 million is equal to 50,000. Our B value is 2. And our X value is our unknown. Okay? So we got to figure out how long it's going to take. Now, what that means is we're trying to get our X value by itself. So what I'm going to do here is we're actually going to take this 50,000 and we need to bring it to the other side. Now, what operation is 50,000, or between the 50,000 and the 2? All right, so in order to move it, what do I have to do?
Divide.
Yes, so we're going to divide both sides by 50,000, okay? So on the right side of the equation, we're going to end up with 50,000 divided by 50,000 is what?
0.
Not 0.
Or 1.
1, right? But you have the right idea where they kind of cancel each other out. So we're left with 2x on the right side. On the left side, 50,000 into 2 million. All right, let's figure this out. So 2 million, 2, 3, 4, 5, 6, divided by 1, 2, 3, 4, 40. Okay? So it goes in 40 times. So 40 is equal to 2x. Well, you're right, we would normally use a log to get an exact answer out of this. We're going to go into a table method, a little bit of trial and error. Okay? So let's say, let's get a little box like this. I'm going to make it smaller. And we're going to move it over. We only want the box. So, what I mean by that, what I'm going to do here is I'm going to plug in different x values as if we were graphing it. X was 1, X was 2, X was 3, X was 4, was 5. What would our Y values be? Now we know we're aiming for 40. So we're going to plug these numbers in to see what we get. So if X is 1, what's 2 to the power of 1?
2.
Not quite what we're looking for. What about 2 to the power of 2?
4.
2 to the power of 3?
8.
2 to the power of 4?
16.
Yeah. 5?
32.
Are we there yet? What are we aiming for?
40.
Yeah, right? We need the number to be 40. Let's keep going. To the power of 6?
48.
Well, what were we doing here? Remember, we're multiplying by 2 each time, right?
Also 64.
Yeah, that's right. So, it's going to be the number 64. Now, 40 is going to fall in between that. So we know we have some x value. X is equal to something between 5 and 6. Right? We know it's greater than 5 but less than 6. Depending how exact your teacher wants your answer to be, we might have to do some trial and error. What we can do by trial and error is we can test a couple values out. 2 to the power, where's my power button? There we go. 2 to the power of, let's say, 5.5. We go right in the middle. 45. So a little high. So I might jump down again. Okay. 2 to the power of 5.3. Oh, that one's close, right? 2 to the power of 5.4. It's a little much. So we know it's between 5.3 and 5.4. Okay, so we've got a little more exact now. We know it's between 5.3 and 5.4. Okay. Now, what these values stand for, okay, is the number of periods that are going to need to pass in between 50,000 and 2 million. Okay, so even though it's only a day, so what we're going to do is we're going to round this. Okay, we're going to say it's 5.3. 5.3 cycles. All right, needed to happen in order to get to 200 million. Okay, we had to pass through 5.3 cycles. Now, what we got to figure out is, right now we're measured in days, right? Everything's being measured in days. So we got to figure out how many hours 5.3 cycles in the course of 24 hours takes up. And what I mean by that is, because we knew we had a day separating them, okay, we had how many hours separating these two, let's say? 24. And in the course of 24 hours, there's 5 cycles, apparently. So, 24, so x is actually going to be our 24 divided by our 5.3. That's going to tell us how many hours, roughly, that we're going to need. So, 24 divided 5.3, we'll round it, right? 4.5. So, the doubling time for this, the double, is roughly every 4.5 hours our thing is going to double. Okay, so that one's a little confusing. There's quite a bit of work we needed to do to that one. Solve it. Okay, same question, but they're giving us a bit of a different formula. Now we're used to y is equal to a, b, x. Since they know it's doubling time and they're trying to find out specifically doubling time, what they've done is they've replaced it with y equals still a as our initial value. We know b will be doubling, okay, and t over d. Okay, and these variables, t is time passed, okay, and d is doubling time. Okay, so same numbers. Our y was 2 million. Our initial value was 50,000. And time passed was 24 hours, and d is what we were trying to find out. So same idea, we need to move 50,000 to the other side, so we divide by 50,000. What are we going to get? Do you remember?
40.
Yep. So we end up with 40 is equal to now 2 to the power of 24 over d. Now, since we have a fraction, we're going to write this as a radical. In other words, we're going to get 40 is equal to the d root of 2 to the power of 24, correct? All right, well, let's get rid of this power of 24 here. This power of 24, how would I get rid of the power of 24? What do I need to do to each side?
Square root.
Not square root, but the
24.
24th root. I gotta find the 24th root of both sides of the equation. On the right side, that'll cancel it out for us. Okay, so these two will cancel out, and what we'll be left with is on the right side the d root of the number 2. And 40 to the 24th root. I'm going to bring out our calculators here. Shift 40 to the 24th root. 1.166, let's say. Okay? So we get 1.166. Okay. Now we're trialing error for d. Same idea, we maybe set up a t-chart. Our d values and our y values. We know we need our y value to be 1.16. Okay. Now remember, doubling time. Do you remember what we got in the question before? What the doubling time needed to be in hours?
1.3.
Yeah, I think we got 4.5. I think we wanted to. So let's try doubling time of 4 hours and a doubling time of 5 hours. So in other words, when d is 4 and when d is 5. Right, so we take out our calculator. 2 root 4 gives me a number that's a little too big. So I try 2 root 5. 2 root 5 gives me a number. It's too. What was the other one? Was the other one too big also?
Yeah.
Sorry, and this one's too small. So we know it's in between 4 and 5. So, like we tried before, let's try our doubling time of 4.5 to see if we get the right answer. Okay. The number 2 to the root of 4.5 gives me 1.166. So, this is another way to do it. Because we got numbers that are too big, and we knew that d needed to be a number between 4 and 5, and we found out that d was roughly 4.5. We found the 4.5 root of 2, we got 1.166, which is the same answer we did in the other one. Only difference being is I didn't have to divide by my 5.3, my 24 divided by 5.3. I got right to the answer. Now, both of these end up working, so it doesn't really matter. So now, with that being said, we're going to use the same formula we used in the second one here. Let's just jump over, add another page. Okay, and what we're going to do here, same type of question, but this time they want to know 1 million. So if there's 1 million people, is equal to, and we'll use that doubling time formula again. We know we started at 50,000, right? 2. Now, they're actually looking for the amount of time passed because we know doubling time is 4.5. We know d is that, right? We got to figure out how much time has passed. So, same idea. Move 50,000 to the other side of the equation. Okay. That's going to give us 20, I believe. So this gives us 2 to the power of t over 4.5. Now this one we can set up a little easier, I suppose. This becomes 20 is equal to, we write this as a radical, it's the 4.5 root of 2 to the power of t. That's right. We put that in a calculator, what do we get? I think we get 1.166. Let's try it out. 2 to the root of 4.5 equals 1.166. Perfect. So now we're left with 1.166 to the power of t. Okay. So now we got to figure out how much time has passed. And we're talking about in hours, right? We knew in 24 hours how much time has passed. How far would we have gotten to? What was our number? How many million bacteria were there in 24 hours? Or after one day? Remember day 3 and day 4? How many million were on day 4?
Day 4 is 2 million.
Yeah. So we're talking about 2 million, okay? So we know we got to put a t-value that's less than 24. So I can, again, make a little chart. T-values and y-values. We know we got to go less than 24, so maybe we want to try like 18 and then the number 19 and maybe 20. We want to test those out with that 1.166. So 1.166 to the power of 18 doesn't give us the 20 we're looking for here. Let's try it again. 1.166 to the power of 19 still doesn't give us a 20. 1.166 to the power of 20 gives us too high. So let's try this. 1.166 to the power of 19.5, halfway between. And we're looking at almost 20, 19.98, okay? So we know that in between here, we discovered at 19.5, we were approximately at the number 20. So we're looking at approximately 19.5 hours, which makes sense because if we think about it, we're talking about double time, right?
Yeah.
So half of 2 million is our original, 1 million. So in other words, we need to double a million to get to 2 million. And if we know the doubling time was how long? 4.5. If it took 24 hours to get to 2 million, I subtract 4.5 hours from 24, I get 19.5 hours. So using this method, we can find an exact time. Okay? But there's always a real fast way of just subtracting by the doubling time in order to solve it.